We're going to draw the lowest structure and determine the VSEPR geometry for carbon dioxide. Let's start with counting up the valence electrons. Carbon brings in 4 valence electrons, oxygen brings in 6, and there's 2 of them. So that's a total of 12 from the oxygen plus the 4, going to give us 16 total valence electrons. Carbon is less electronegative than oxygen, so we're going to put carbon in the center, surrounded with the 2 oxygens. We're going to connect the 2 terminal atoms to the central atom. That's going to use up 4 of our valence electrons to put into those bonding pairs. So we're down to 12 electrons. Next, we'll give the octet to the terminal atoms. They're more electronegative, so we'll do that. That's going to use up the remaining 12 electrons. Now the central atom needs more electrons, so when that's the case, we can take lone pairs from the terminal atoms and move them into bonding pairs to make double and triple bonds. So we can do that, one from each, and create a double bond between each. This turns out the formal charge is going to be 0 on all of them, so this is your lowest structure for carbon dioxide. There are other ways to draw it, but I've already made videos on that, so you can look up how to do formal charge and you'll see that this is the correct way. Now let's go into VSEPR to determine the geometry, find the central atom, and determine how many regions of electron densities there are surrounding that central atom. In this case, there's 2 regions of electron densities. Right? You're not counting the number of electron pairs because this pair and that pair are not able to separate from each other. So that's just counted as one region or one domain. So there's 2 total domains. So we're going to go down here. When you have 2 total domains around the central atom, the farthest they can be separated is 180 degrees from each other. So the answer here is linear.